Hello and welcome back. This is going to be video number 4 for week 1. Even though week 1 is almost over, do keep in mind I am aware that I'm sitting at Dropbox for Tuesday. I realize that since this is only coming out now, you may not be able to juggle your schedule to follow this video between now and Tuesday if you had other plans or something. So don't worry if you don't have all of the week 1 videos done. For the Tuesday screenshot Dropbox. That would be ideal, but and I suppose unless you happen to listen to the beginning of this, you're not hearing this message, but I've put it in email out to all of you, and I've put it on the instructions for the Dropbox as well, so hopefully nobody's stressing out about that. But I do hope you are getting to this as soon as possible after Tuesday if you haven't done it by this Tuesday. What we're going to do in this video is create and run your first assembly language program. Let me zoom in a little bit in our notes. So there's really not much other than to just kind of get down to it. I will probably be showing you a few Linux tidbits and give you other tips and things along the way, but I'm going to try and minimize the times I go off on a tangent and mainly focus on having you just write the program and build it and run it, and hopefully at least understand a little bit of what you're doing along the way. You won't understand, or it's fine that you don't know everything that I'm doing here as far as what's going on in the assembly language itself. I just mainly want you to get through the process where you've actually written the program, saved the file, run the assembler, run the linker, and then run your new program that you wrote in assembly language. And then next week we'll start getting down to the nitty-gritty of understanding what you did. But I do want you to have some idea what you're doing as we're going along. So otherwise this video could probably take 5 minutes. I could say type this into a text editor, run this command, run that command, and boom, 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 you'd be done. But I do want you to have some understanding of what you're doing as we go along. So with that in mind, let's get down to it. So bring up your VirtualBox Manager. If your machine is currently in a save state, as you can see my one for this class is currently saved, go ahead and start it back up. And give that a couple seconds to restore. And with your virtual machine restored, oops, I think I mistyped my password. There we go. With that restored, now here we are back in the virtual machine. This is pretty much where we ended up with last video, having installed all the software we needed and so forth. So let's go ahead and get down to it. I'm going to use the gedit editor. It's fine if you prefer VI or Nano. You might want to look into assembly language syntax highlighting for Nano. I'm going to show you how to do it for gedit. Maybe Nano has it by default. I don't know. Like I say, I'm not a Nano user, so I'm not sure what to expect from Nano normally. But if we want to write a assembly language program, we're going to want to create that in a text editor. So I'm going to do that here in my csc314 classwork folder. One thing I will point out, just since it came up on my terminal window here, you'll notice that it has this 1 in brackets plus done gedit. That's a message coming back because earlier we ran gedit in the background. We go back far enough to the last time I ran. So remember I showed you how to use ampersand to run the gedit so that it detaches from the terminal. It's not completely detached. The terminal is kind of aware of its existence, and gedit is aware of the terminal it came from. And so because I exited gedit there, it sent this message to the terminal, and that's what's appearing there. So sometimes you'll see that when you have programs that are running in the background or detached from a terminal, they may still send messages to the terminal that kind of get mixed in with other things you're doing in the terminal. You just kind of have to get used to that. or you may want to open separate terminal windows to do some tasks so you don't get those messages mixed in with other commands that you're doing on the terminal. But at any rate, here we are in my csc314 classwork folder. You might want to create separate folders like week 1, week 2 or something for classwork, just to kind of keep things a little more organized. But for now, I'm just going to use this folder. And so let's go ahead and say gedit first assembly program, ASM for short, program.asm. Just kind of traditionally, .asm represents an assembly file. You could actually do this without using the file extension at all, but might as well be consistent about how we indicate what kind of file this is. So, and I'm going to use the ampersand to detach the gedit from this terminal. And again, see this message here, that came as a result of using the ampersand to detach that process. And when that process exits, you'll get something similar to this. All right, so now I have my gedit open, and I'm going to go ahead and make that window a little larger. And right now, I'm going to, before I get started here, I'm going to show you a few options within gedit that if you're using gedit, I certainly encourage you to use. Displaying line numbers, overview map maybe. If you've used other editors, you may have seen something that's like it's almost like a mini map of the entire text file. Kind of helps you keep oriented as to where you are. I kind of like this grid pattern, so I throw it in. And highlighting current line, highlighting matching brackets, always very useful. And then there's the great tab versus spaces debate. I fall very much on the side of spaces, so if you like tabs better than spaces, you're a very, very evil person. No, it's really up to you what you prefer. I just think using spaces gives me a lot more control over the indentation and format of my programs. It's just easier. I generally like to have automatic indentation, and might as well have it create backups when you save, and also do autosaves just in case you screw up and lose some work or something. You might as well do some autosaves. Font and colors, you do have a number of themes here, so you might pick out your theme. I generally prefer darker themes. Actually, I think Cobalt is the one I usually like, so I'm going to go with that. And to make things more readable in the video, I'm going to bump up my font size a bit. And that's even more useful when I'm on a projector in a classroom, but even for the videos, I think having a larger font size is not a bad idea. Gedit does have a number of plugins that you might want to Google about and see if there's other plugins that you might want to install. Some of these are already available and you can just try them out. But I'm not going to get into any details there. But there is one other thing I want to do for gedit. And let's see. First, I'm going to put just a few elements of a assembly language program here. You can go ahead and do this as well. This isn't the whole thing yet, but just the beginnings of an assembly language program, and I'm going to go ahead and save that. Now, right now, I don't have syntax highlighting for assembly language. If we go into the View menu here, Highlight Mode, you'll notice it has C, it has almost every language you've ever heard of, but it doesn't by default bring in an assembly language highlighter of any kind. So I'm going to go ahead and get that. So let's come back over to the terminal window, and we need to download a file with a command called wget is the easy way to do this. And I need to go where I have that command written down. Actually, I'm looking at my clone computer, my clone version of this machine where I've already done this to make sure everything's working right for purposes of this video. So let me copy and paste. See if oops, I got the return, so I didn't get a chance to let it wait. But there's the command right there, wget HTTP, this HTTP address going out to this specific file. That's just going to get that file and drop it right here in the current folder. So now I have this asmintel.lang file, and now I just have to put that in the right place and restart gedit, and then it will have the syntax highlighting for the assembly language. So we need a sudo for this because we're copying it to an administrative folder or a system folder, and we want to copy that file that we just downloaded, and I'm going to go ahead and maximize this terminal window. 3.0 / language specs. So this is the whole thing here. That's where you want to copy that file to. So, oops, and I mistyped the copy command. So this is your copy command in Linux. So again, the sudo command is saying that you want the sudo or the super user to do the command that comes after it. The command coming after it is copy this file from the current folder to this system folder here, and hit return. It wants my super user password. There we go. And now that file has been copied there. Now if I exit and restart gedit, we should see assembly language highlighting. So let's exit. And if I arrow up to my gedit command, there I have gedit on that file. And there we go. I don't like this highlighting as well. I guess that's not the theme that I wanted. Let's try Solarized Dark, I think, gives a little bit better. Actually Oblivion there. I kind of like the blues, but I think Oblivion is maybe the most readable one here. If we went back to classic, I don't like white background, so I think that one's pretty good. There might be, I think there was another theme I used to use a while back. I might have to that might be a theme I'll have to download at some point, but this is not too bad. So now you can see that we have some syntax highlighting here. In particular, well, do I like that? Yeah, that one's probably all right. I did have a typo there. All right. So you can see that this symbol start is being highlighted. This EDX here is being highlighted. That's the name of a register. That's something that you're going to be learning about a lot more later on. I'll be explaining them a little bit today, but not in a lot of detail. I don't know. I'm kind of torn. Yeah, I think that's better. All right, so one other thing I might want to do. Yeah, I think if I use the bold version of the font, again, that should help make it a little bit more readable here. Okay, I think this is pretty good. So now we have syntax highlighting, and we can continue on with creating our assembly language program. So first I want to talk about this section keyword up here. So So the sections that you create in an assembly language program, they basically define distinct regions of memory for your executable program. That is the binary version of your program. And so .text, and there's a bit about this in the notes as well, but the .text section is read-only and typically used for the actual instructions of your program. Why is it called .text? Why isn't it called, I don't know, .instructions or .program or something? I actually don't know the history behind that, but .text is just traditionally what that is called. It's what the linker is going to expect and so forth, so let's just call it that and live with it. So next, we have this global underscore start. So the global keyword will make symbols in your assembly program visible to the linker. So don't worry too much if you don't know what the linker is yet. Just figure there's basically two steps to building an assembly language program. There is assembling and then there is linking. The linker is the one that knows how to take the pieces of binary machine code and put it together into the proper format for a standalone executable file. And it doesn't need to know all of the symbols that might be defined in your assembly language program, but it needs to know some of them, such as this start symbol, because the start symbol here is kind of by default where the linker is going to expect your program, the instructions of your program, literally to start. So it needs to know where that symbol is, or that symbol actually exists in your program as something the linker can find. So we use the keyword global underscore start to make the underscore start symbol visible to the linker. All right. Now, what does it mean when we do this syntax of something colon? All right, so syntax of something. Incidentally, if you didn't catch on, semicolons are how you start comments in this particular variation of assembly language. So everything I'm starting with a semicolon here is a comment. And by the way, I do think you should, not just copy the code here. You should go ahead and type comments. I mean, you don't have to use my exact wording, but put in the same comments, because, if you type these comments in, it's just going to make it sink in, and you'll remember that much better what's going on, and it'll enhance your understanding down the road. So go ahead and recreate this program, including comments, kind of as we go. You can always pause if I'm going too fast and you need to catch up. So the syntax of something colon creates a symbol something, okay, whatever something is. All right, so here I'm talking about underscore start. That's the symbol. All right, and that symbol represents the address of the next byte of memory that your program will use, whatever that byte may be. Typically part of an instruction or simply data. Okay, so when I do this start colon here, I'm really creating an address that's going to represent the location in memory of this instruction right here, this MOV, which is move. I don't know why they feel like they have to have 3-letter instruction names, but they do. So you drop the E from the word move, you get MOV, and that's the instruction move. So, and that's an instruction that's saying move something from one place to another place. We'll understand a little bit more about what that exactly is doing later. Think of it a little bit like an assignment statement in C, but not quite. There are definitely some important differences. But the point is that this start symbol basically just represents the address of where this instruction is. So underscore start symbol represents the address. And I want to say, when I say address, for now, think pointer. So if you remember about pointers from Computer Science 2, that they are actually numbers representing specific locations in memory. That's basically what we're talking about. So in a sense, start is a pointer, but it's a constant pointer. It's going to specifically point to this location and nothing else. The location of this actual binary instruction where it happens to appear in memory when your program is running. So the start symbol represents the address. So when I say address, think pointer of this instruction. And just to be a little bit more specific, let me add to that comment. Specifically, address of first byte of this instruction. Because to represent this entire instruction will take multiple bytes out of memory. So I'm writing a pretty short program here, but it's important for you to at least have a sense of what's going on. I don't want to be just typing in a program and have you copy what I do and have no idea what's going on. So now let's throw a few more instructions down here. So I want, let's see, I want move EC, oops, did I click, move ECX, comma, MSG, move EBX, 1, move EAX 4, and then I have a different instruction, int OX80. So let me add a little bit of context here. So move instructions copy data to and from memory and or registers. All right, and registers are going to be particularly the new concept here. But for now, and you'll notice syntax highlighting has helped us out here. The name of that one should have been ECX. Notice with S it's not highlighted, but it recognizes it as a register name there. So we have EAX, EBX, and so forth. Our registers. Let's just leave it at that. And what we are doing here is moving constants into those registers. Now these constants will actually be data stored as part of each of these instructions. So these constants themselves will be represented as a byte or bytes of data in memory that come right after the bytes that represent the first parts of each of these instructions. And that data will be copied from that place in memory into the registers. So, and that's what all of these are doing, except message lang and message are going to be substituted by numbers by the assembler later on. They haven't really been defined yet. We're going to define those in a moment. Let me go ahead and separate a line here for this last instruction. Int stands for interrupt, and will cause basically it will cause the computer to jump execution to a system routine, okay, or a system call. And I might as well give you a little more detail. So in this case, it is going to do a sys write. If you want to start Googling about stuff, just kind of fill in your understanding a little bit. I certainly would encourage that. But we will be getting into more details. So basically what these 5 instructions are doing are setting up, well, the first 4 instructions are setting up the system call. This is going to trigger the system call. And the system call is actually going to print a message to standard out, basically to the terminal that you run your program in. And that's pretty much all there is to that. And what causes it to be a syswrite are what we are putting in these 2 registers here. These 2 registers are storing the location and size of the message that's going to be printed. So, and this is all stuff that we're going to get into more detail in later on, how syscalls work and so forth. But for now, let's just go on and keep writing the program. I want you to be somewhat oriented, but I'm not going to try and have you understand every detail of what's going on. All right, so I'm going to do a few more commands, and then that's it for our program. EBX, comma 0, and move EAX, comma 1, and int OX80. And another system call, this time to the sys exit to end the program cleanly. And again, the system call is set up by these 2 statements. And once again, I mistyped move. And there we go. So that's all the instructions of the program, but we do need some data. So to get data, I'm going to create another section of my program called section.data. Seems to be a little bit more sensibly named than section.text, but so that's kind of good. All right, so we have another section for data. And in this section, we just have a couple lines to create. First, I'm going to do MSG, and then DB, and then stuff in text. I'm going to just say, what's up, doc, question mark, like so. And so what's going on here? Well, we're actually, this line defines another symbol. It's a little bit of a different way than using start colon, but this line is defining another symbol, which is an address, okay, which will point to the first byte of data specified after DB. Okay, now what is DB? DB just stands for data bytes. Okay, so we're basically saying that from the beginning of this section called data in memory, we just want to have some specific bytes defined, and we're defining them using a text string here in the assembly language, but this is really just specifying the numeric values of the ASCII codes of these characters. Now, So the bytes of data are the ASCII codes of the characters in the text string. Okay? And my comments get long, so I need to make my window wider so we don't keep wrapping around. All right, so literally there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, specifically 15 bytes of memory used up here, and they will have specific ASCII codes. I could actually put this as a list of ASCII codes. In fact, if we pull up the ASCII table, any ASCII table will do. Here's an ASCII table. So let's look up, where's W? Capital W. So the ASCII code for W in decimal is 87. So over here, instead of that W, I could put an 87. Right? So, and you can chain, like you could write actual numbers, as long as they're 1-byte numbers, separated by commas, mix that up, chain that together with text inside double quotes, and you're specifying the same bytes. So like that lowercase h, if we go back, whoops, go back to the ASCII table and find lowercase h, that's 104. Then instead of any h inside the quotes, I could have a 104 here, and so on. This is exactly the same as if I had just left the w and the h inside the quotes there. So, so just to provide some additional concept, can string numbers from 0 to 255, i.e. 1-byte numbers with commas, or put ASCII text inside quotes. Either way, that lets us just set up that data in memory, okay, so that when our program actually finally becomes an executable program, you know, there will actually be bytes in that data file that are these specific ASCII codes, and when that program gets loaded into memory, there will be a specific place in memory whose address is given by this symbol here, and so if we want to actually access that location in memory, we can to get at that data, such as if we want to print that message out. Okay, so now we're going to define one more symbol here in our data section, and I'm going to call this one message len for the length of the message. And the syntax here is a little bit strange. $ minus, oh, whoops. First I want to say EQU $ minus MSG. Make sure, yeah, that's what I wanted. All right, so what's going on with this line? This is a little bit strange, but just so you're aware. So the EQU, this is all stuff that the assembler, when it's reading your text file assembly language program, is going to be figuring out for you. These things are not instructions that execute when your program runs. This stuff up here, these are instructions that execute when your program actually runs. These are things that you're defining for the assembler so that it can kind of keep things straight. We're defining this as the address of this byte of data right here, so you know where this sequence of bytes starts. That's what MSG is. This, I'm just defining a symbol for the assembler that will store how many bytes I've got here. And the way that's working is I'm just saying this symbol equals whatever this formula comes to. What is this formula? Well, $, $sign here represents the current byte position or address in what will ultimately be the binary executable file. Okay? So I'm just going to put that down there so I have room enough for my long comments. Minus is just subtraction, and MSG is already defined as the address of the first byte of the above text data. All right. So if we take the current address, in other words, the address, like if I created more data on this line, $ would be the address of that data. But I'm not creating new data there. I'm just defining a symbol. But $ is basically the address of the next byte that would come after the ASCII code for this question mark. That's what that $ is. And that's what $ means wherever it appears in your assembly language program in this kind of context. It's representing the current byte position or the current address. And if we subtract the address of the first byte, if we subtract the address of that byte right there, where that W is stored, capital W is stored, then the difference between those addresses is the length of this text that I've created here, right? So that way, if I decided to change my text to, I don't know, what's down, doc? Okay, now it's too longer. Well, when the assembler compiles or builds your program, the value of message len here will equal the complete length of this string. And that's important because I use message len up here and put it into this register so that the syswrite syscall will know how many bytes of data it's going to write out. I put the address of the first byte of text data into this register so that the syswrite system call will know where the message actually starts. So it knows where it starts and how many to print out. So now, instead of just having the first program just there, you have hopefully a pretty good sense of what it's going to do and how it's going to work. So now if I save this, and if I haven't made any typos or other errors in there, this should all work just fine. Let's come over to our terminal window and see, we got a message out of gedit here, background message. Not even sure why it's giving us that message specifically. It's not really a problem, but again, you may want to run gedit from a separate terminal window just so you don't get cluttered up with these extra messages that it's sending. So here we go, and there's our FirstAssemblyProgram.asm. So now how do we build this thing? Well, we're going to build this with the nasm command. That's your assembler. And we need to give it an option because what we're working in here is 32-bit assembly language. So we need to give it that format, which is ELF32. Don't worry about why it's ELF, but 32 there is kind of the critical part. And then we need to give it the name of the assembly program that we want it to build. All right, so far so good. And if we run that, hopefully we don't get any errors. We have an error on line 14. Symbol message len undefined. What did I do? Okay, yeah, case sensitive message len with a capital L because I used capital L down there. So let's fix that. Save, come back. And now I can just arrow up instead of retyping that command. And there we go, run it again, and there we go. It doesn't come back with an error, and if you're used to, for example, using GCC, when you don't get any messages from GCC, that generally means it was able to build your program. So if we do an ls, we can see what was created. And here's the file that nasm created, a .o file. That's the object file. This is not yet an executable program. It basically has the binary instructions of an executable program for your program, but it's not all put together in a form that you can just run as a standalone executable file. So that's what we're going to do next. And to do that, we need to run the linker. Now, a linker is something that you may or may not have already learned about at all in your previous programming classes. But a linker, if you were doing C programming, a linker was always there in the background, hiding. Because there's really two steps to building a C program. There's the compile, and then there's the link step. Normally, a compiler like GCC or any other compiler you're used to using will just take care of calling the linker immediately after it's done compiling, unless you give it special options to tell it not to do that. So, and you may or may not have explored what the linker is and what it does in your previous classes. Kind of depends on your instructor. But we're going to just go ahead and use the linker directly. Later on, we'll see how we can actually use the GCC compiler command to do the linking for us. We still have to do our own assembly with the NASM command, but we can use GCC to do the linking, and it'll figure out what needs to be done as far as linking goes. But for right now, we're going to do the linking manually with the link command. So let's see. Okay, so to do the linking, the link command is LD, all right, and we need to tell it what format we're working with. And again, we're building 32-bit applications, which will run fine on a 64-bit machine, just not the other way around. But we do need to tell it that that's what we're doing. So here, the way you specify that format to the linker looks a little different. Whoops, not 3elf. Still has the elf in there, but underscore I386. So that -m elf underscore I386, that's an option to tell it that we're doing basically a 32-bit program, 32-bit executable. And then we need to tell it what to link, which is that object file. And initially, we are not linking in any libraries. This is just a very standalone, very minimal assembly language program. So there's no libraries to link in here. So all we need to do is give it the object file. So really all this is going to do is take our object file and turn it into a properly formatted, standalone executable file for a Linux machine on a 386 32-bit Linux machine. Which will run just fine on a 64-bit Linux machine, which is what you probably have installed here if you followed the previous videos. All right, so we're going to do this linking step and hit return. And there it goes. It went off without an error message. That's a good sign. And if we do an ls now, lo and behold, you get that familiar a.out that you used to get from compiling C programs. Now you know that a.out is really created by the linker, not by GCC. GCC calls the linker to create a.out. And we can run a.out with /a.out. Incidentally, you can't just say a.out directly here because we have not set up our Linux system to look in the current working folder for command names. So we actually have to give a path to the command name, and you can use dot, meaning the current folder, and then /a.out. And that's a path to a.out, and since it's a path, it's not going to, since it's a specific path to a specific file, it doesn't have to search anywhere for a command of that name, and only look in the places where it's willing to search. So this will run it just fine, and boom, that runs it, and lo and behold, we get the message, "What's down, Doc?" And if we go back to our program, we see that that makes sense. We're doing a syswrite call. Basically, these three instructions here are what make it a syswrite call, but the syswrite call also needs these two things to know what to write and how much to write. So this is telling it where the message starts, this is telling it how long the message is, and here is the actual data of the message, which is interpreted simply as ASCII text. So 87, that's a capital W, 104, that's a lowercase h. We get the ASCII codes for all these things here in the string. So far so good. And we ran the program, and sure enough, it printed that message, it exited cleanly, and gave us back the command prompt. It did not drop the command prompt down to the next line, specifically because we did not give it a new line character to print. But let's go ahead and do that as the last thing we do today. Now, you might be tempted to do this. Put a /n in there because that's what you know from C programming, right? But the assembler doesn't know what /n means inside of a string, so you can't do that. But we can just string bytes together here. So if you really want a new line character, all you need is a 10. Or if you want to do it in hexadecimal, we can say 0x 0a. Like that. Either way, both of these mean 10s. If you put 0x in front of a number, then it's a hexadecimal number. Don't worry if you don't know what hexadecimal is yet. We'll be learning that later. Or again, we could just put this down as a 10 if we want to put these in decimal. And we could have written these as hexadecimals as well. We could have done all of this up to here as a string, but there's no way to put that /n in there, so we just do that by specifying the actual numerical value of the ASCII code of the new line character. So again, if you weren't made familiar with ASCII codes previously, if we scroll back up here in this ASCII table, you see that 10 is here. They're calling it line feed, but basically it's the line. It's the new line character. So there we go. That is all we need to do. And again, because we're just tacking this on to this list of data bytes that message is pointing to the first byte of, again, message len is going to be calculated to be the difference between the current byte right here, right where this line starts basically, and the address message. So it's calculating the difference between 87 and a pointer to the next byte after this. So it'll be one bigger than it was before to accommodate that extra byte. So message length will have the right value. That's what the assembler will put in for that as a constant, and the address of message goes in for a constant here. So it should still work if we run this. So let's go ahead and fire that up. So again, we need to redo the nasm command, like so. And then we need to redo the linker command, like so. And finally, we can run a.out, like so. What's down, Doc? Okay, so actually I said that was the last thing. One final thing I want you to do. So this is a little bit like the last thing you want to do, and get a screenshot to show you did this. Let's redo the linker command, but I want you to add a -o option. You'll notice that the linker command takes a lot of options that are similar to what you may have seen with GCC. -o option is something that GCC actually passes on to the linker. -o just basically says, what do I want my final executable file to be named? And here I want to maybe call it FirstAssemblyProgram, so that it matches my source file and my .o file. So this will create this program instead of a.out. I suppose you could just copy a.out to a different file name, but why go through the extra step? Just use the -o option here and give your program the name you want it to actually have instead of a.out. And there we go. And now if I do an ls, you'll notice that we have another executable file here, FirstAssemblyProgram, and we can run that with /FirstAssemblyProgram, and it'll do the same thing. There we go. What's down, Doc? All right, so if you followed everything up to this point, you have now created your first assembly language program, and hopefully you even understand a little bit about what's going on inside that program. And we're going to learn what registers really are and how they're similar to but different from variables, and why it's really more true to say that this thing is a variable than this thing, and all kinds of mysterious stuff like that. But that's for next week and the weeks to come. Right now, if you've gotten through this, then that's everything I really hoped that we would finish in the first week. Hopefully most of you get to this point by Tuesday, but I understand if you don't. And until next video or the next time you hear from me, I'm over and out.